Hello, this is Benjamin Mayinger. I'm a member of the Using Ocean-Going Robots to Observe Wave Conditions team, specifically the CS team, and today I'm going to be showing you the block checkoff for the Directional Wave Spectra processing block, and you can see it's been assigned to me. We have more than 2 properties per interface, so let's get into the implementation and prove that all these properties hold. So first off, basically what this block is doing is it's taking parameterized wave data, meaning it's been passed through a Fourier series to produce these spectra and co-spectra, and then from these values we can actually calculate a directional spectra. These are reference papers that our project sponsors kind of provided with us. These guys do it a little differently, but we kind of adapted their work and got it working for us, so let's get into it. So before we begin, let's actually look at our input and prove that all these properties hold. So first off, it is required for the program to validate input and handle bad input by producing a relevant error message, so we're going to do that first. I'm just going to show you the directory here. We're inside this folder. We got bad input. That's what I'm going to pass it. This input is formatted incorrectly. If you look at, this is what our real data should look like. It's 128 by 12 matrix. So yeah. So let's just pass that in. So we're going to call this script by doing Python directional.py, and then we're going to do bad input.csv, and we should get, yep, provided input file doesn't match expected data format. So that's just one case of bad input. Let's say we pass it a file that doesn't exist. There's no bad input.txt. The provided input file doesn't exist. Okay, so now let's give it a file that exists, but then also pass another file, which would be too many files, of course. So too many arguments are given. We get, like, explains how to call. Now let's do no input, and too few arguments are given. So that's all the cases of bad input that we can really provide. So now that we have asserted that this works, we can actually get into what our input should look like. So the CSV input file contains a Fourier components as a function of frequency defined by the rows. So this is a little bit confusing, but if we look into our actual good data, it's kind of a little bit hard to see, but there are 12 components here, 128, and actually a better way to show this is these correspond to the different column numbers. So we have just a row number, we have a frequency in hertz, and then we have our different Fourier components, including these are, I guess, the crucial variables that we really care about for creating a directional spectrum, using that algorithm provided by this paper here. So now let's actually get into some good input. So let's say we pass params3. We get some runtime warnings, but not a big issue. So now that we've run the script, what we'll see is we have a new file created here, d_params3, which is a CSV file. So let's look at this file. So, I mean, again, really hard to see what's going on here, but you're gonna have to kind of trust me for a sec. So let's get back to our properties. So so it is CSV input, it's format CSV, we got matrix of float values, it's passed between program modules as a file using the command line. So these all hold. So now let's look at the output and prove that our output's looking good. So output data is formatted as a directional spectrum with 3 key components. Each point in the data represents an energy density at a specific period and direction in relation to the glider. So I can't necessarily prove that just by showing you those numbers, but we will pass it into the directional visualizer so that we can actually see that that's happening. And data is a matrix of float values describing directional wave parameters, and then columns define directional bins in 5-degree increments. And then, yeah, while rows correlate to wave period from a max of 0 to 0.7. So we already showed that this is working, and then finally values stored in CSV files and passed to the visualization framework module as a command line argument. So now that we've created this file, just go back a directory and then put it into our directional visualization directory. So we gotta get into there as well. And now we can call polar.py with dparams3, our newly created spectrum. And what we'll see is it's going to be a 180 slice here. So basically the example data that was parameterized was a 180 swell, kind of centered, like more energy dense on the west kind of axis, I guess. So first off, just the fact that that works, that we can pass that into the directional visualizer, kind of asserts that the data is formatted correctly, and holds these things to be true. It is a directional spectrum of 3 components. The period is defined by the rows, so we can go back here. Again, it's hard to see just looking at this, but each row defines a period, and then each column is a direction, in 5-degree increments. There's 72 of them. And we can actually, let's get into the code just to continue to make sense of this. So basically what's happening here is this is where we do our real calculation. So we read in our input, and then using the parameters, which can be accessed just using this kind of array notation, that we calculate R1, R2, theta 1, theta 2, which again are these values, and then we push them into this function, which is a function of frequency and direction. So for a given direction, which is defined in our for loop here, as in radians, from 5 to 365 and 72 bins, which is important because they're 5-degree increments, then we do the calculation and append it to the row. So basically we're creating rows that have 72 columns, and then we append the row to our spectrum, which is our main data variable, and then we write the spectrum to a CSV file. So that's kind of like the gist of how this works. And yeah, I mean, that's basically it. All of these properties are true. They all were implemented, and I'd like to thank you for watching my checkoff. I know they're probably pretty boring to watch a ton of these in a row, but yeah, I hope you enjoyed. Thank you.